So for starting, just one announcement. We are trying to organize a social dinner for the conference. So the idea is to meet outside the IM at 8 p.m.
And then we go to the center.
In front of him. Social dinner. The idea is to go and have some dinner in some German place in the center. Who wants to come just to reserve, just to make a reservation? Just do you think that you don't come? Michael?
Eight o'clock.
Siamo tipo 10, 12.
Sì, 10.
Ok, thank you. Let's
Okay. So it's a pleasure to introduce Professor Yongnam Lee from KAIST. He will talk about Q-Gorenstein deformation and its application.
Okay, so thank you very much for the invitations. Yeah, this is my second visit to Bonn, but first time I never visited to this side. I only stayed to the other side. Okay, so today I would like to talk about this Q-Gorenstein deformations and its applications. This is a joint work with Noboru Nakayama at the LIMS in Kyoto University. We are actually developing the very general theory of Q-Gorenstein deformation for arbitrary scheme of a complete local link to apply the mixed characteristic. But today I do not want to do very general theory, so I want to do rather special thing today. Okay, so because if you working with the mixed characteristic, complete local ring with the mixed characteristic, then you can compare with the something like a theory of characteristic 0 with the theory of finite characteristic. But I do not want to talk to these things.
Why do you restrict yourself to scheme?
Because then we can apply to especially some scheme of a finite characteristic.
So why not algebraic space?
Not algebraic space, but something like, for example, the one very explicit application is some construction of a very special surface of general type in positive characteristics, but using some theory from the characteristic 0. Okay, so anyway, so now considering on P1, so let me start by some very easy example of the surface case. So on P1, so then we're considering this extension of the vector bundle over length 2. And then from this extension, I mean, we can have this family by using this extension of this length 2 vector bundles. So then our general special fiber is the Hirschsprung surface, but general fiber is the P1 cross P1. And then if we can construct the -4 curve in the F4, so then, so this is just construction. -4 curve in the central fiber. So then we have this phi, and then pi. Inverse 0 is the some normal surface, which is the cone over rational normal curve of degree 4. So, but the general fiber is still P1 cross P1. In this example, if we considering that this relative canonical dualizing sheaf, so then this not same, so it means especially when we're considering this relative realizing shift as defined as P, and here x0 is the Gorenstein locus of X. Then, I mean, this is not Q Cartier. Because the intersection number is different between general fiber and the central fibers. So let xt, so here t is the same as also spec dBr, so be a normal degeneration of P2. So it means the central fiber is the normal surface and whose general fiber is the P2 over dBr. So in this case, easy to see in fact, this relative realizing shift is Q Cartier always. But it is not true. Sorry. P1 cross P1. Also, if we're considering this P114, the central fiber, then some degeneration of P114 is not Q Cartier. For example, this example is not Q Cartier. But if you do the smoothing to the P2, then actually it's Q Cartier. So some are Q Cartier, some are not. So then we can ask the following question.
Can I ask a question? Why is the positive sign? Why is the 600 obvious?
Oh, you mean this one? Basically here we can, using the P2 is picard number 1, and then if you have a family, and then actually you can extend by using the picard number 1, you can make a Q Cartier. The picard number is very important. So question is given a normal variety X over K is always field, and then what are the conditions for that any deformation of X is a Q-Gorenstein deformation. I still did not define yet what's the Q-Gorenstein deformation meaning, but anyway, later I will define what's the Q-Gorenstein deformation. But we wanted to study this, what's the condition for any deformation is Q-Gorenstein. So for example, this P114 does not satisfy this case, right? Because we know some deformation is Q-Gorenstein, but some are not. Okay, so then, okay, so now let X be a scheme over K.
Sorry, can you remind me definition of Q-Gorenstein? Does it mean it's a Kurban?
Actually, I will define what's the Q-Gorenstein scheme and the Q-Gorenstein morphism and the Q-Gorenstein deformation. Okay, so now X be a scheme, and then we said we suppose the Gorenstein in codimension 1 so for example normal varieties, okay. So then X is Q-Gorenstein at the point P. So we define as a usual. So if there is some neighborhood, open neighborhood of P, and some integer, positive integer R, such that is omega u is R, which is defined as this in the Gorenstein locus, and then push forward to this u. So when I writing x0 means the Gorenstein locus, use is invertible. So this is same as the usual definition. Yeah, I did not assume Cohen-Macaulay here. Yeah, I did not assume Cohen-Macaulay. This is important. Okay. Just this dualizing power is invertible for each point.
So this is the capacity for X being a scheme. Why do we keep supposing X is a scheme? Why don't we suppose that X is an algebraic space?
Oh yeah, we can define. Yeah, but here I already said today I want to do special case because I gave a very general talk, maybe 2 or 3 times, but people don't like that. So I will do the. Yeah, I want to restrict the special case.
Sorry, you don't understand about Cohen-Macaulay?
I do not assume the Cohen-Macaulay here.
No.
Yeah.
Okay.
Okay, so then we say the X is Q-Gorenstein, not the point. That means the Q-Gorenstein at every point. Okay. So then in some papers, give a Cohen-Macaulay condition. Additionally, but we do not give a Cohen-Macaulay condition here. Also, some paper give a more stronger condition. On index 1 cover. So then, I mean, these are stronger than this, and this is stronger than our definitions.
So you're not going to suppose S2.
Huh?
You're not going to suppose S2.
Oh, actually, this definition implies S2
Oh, it does.
because the invertible condition. If the OU is OX is invertible, then every coherent shift is satisfied S2. So this is okay. Okay, so I think the index 1 cover is coming from basically this invertible condition. Then we have this local identification of the so that gives us some index 1 cover. Okay, so then he already asked this remark, and then in fact the X is Q-Gorenstein scheme, then implies S2. Okay. And then, I mean, why we are studying this Q-Gorenstein variety, but this notion of Q-Gorenstein variety is the very important notion in the minimal model theory in characteristic 0, and also important in this moduli theory, especially to compactify some variety of general type of the moduli space. Okay, so let me give an example. Some which are satisfy this condition but not satisfy Cohen-Macaulay condition. This basically we can see easily from using the affine cone.
What are your assumptions on the field? Is algebraic also?
Oh yeah, algebraic field. Yes.
So it's just some obvious application of the duality field that is S2.
Pardon?
It's just some obvious application of duality that is S2.
Duality of the sorry.
To prove that it's S2.
Oh yeah, because basically we can using this invertible, and then OU satisfy S2, and then then the coherent shift has some power of this OU power gives this surjective map, and then you have a kernel, and then back to again to using the again to. So then, very standard proof. You can see in the, for example, Schuller-Singer's old paper. Yeah.
What do you give these are?
By the definition he's written out there, these sheaves omega u square brackets are
Yes.
formal powers are S2.
Yes, I believe.
Right, so he's saying the S2 is, he's saying that O is isomorphic to an S2 sheaf.
Thank you, Miles.
Okay. So then, anyway, let me give an example of this cone. So now choosing S is any projective scheme over K, and A is ample line bundle here. And then suppose S is Gorenstein. And this H and some vanishing of a cohomological condition. Yeah, we can do always. I mean, if we choosing the very sufficiently large ample line bundle, then we have this vanishing condition. So we can choose this kind of a projective scheme. So then, considering this x equal affine cone, which is defined as just spread of okay, so then, in fact, this x satisfies the set condition ST. Yeah, it's always satisfy S2 if we're choosing this way. So, but satisfy this ST condition, this is a set condition, even if this vanishing of the okay. So this cone, in general, does not satisfy Cohen-Macaulay because we need the extra condition of the vanishing. But X is the Q-Gorenstein is equivalent to this. Actually, in this case, Gorenstein we don't need it because that is hard. See? So Q-Gorenstein condition is that this dualizing shape of S, some power is given this power of the ample line bundle, but the Cohen-Macaulay condition is related with the vanishing condition of this cohomology. So these are basically so I mean, to checking the ST condition, we need to check basically only we need to check the singular point of the cone. So, but that is the same as checking this vanishing of local cohomology at that point. And then also we know we can compute this cohomology using this cohomology of S. So maybe I never use this.
Maybe a stupid question, but why you are not requiring the Q-Gorenstein definition that is invertible on the all of U? And just
we define that first at locally, and then Q-Gorenstein means because it might be, in the definition, it might be we have a different R per point. But, yeah.
still don't understand.
Mhm.
Omega x0 to the power r is not logarithmic on U0.
It's 0. Invertible, right? What
So,
do you mean?
J over star is still logarithmic.
Huh? Oh, maybe I forgot to. Yeah, I forgot to maybe. Yeah, no. I said that there is some integer r makes this is invertible. Okay, so okay. Yeah. Anyway, this ST condition can be checked by this vanishing of local cohomology, and also because this x is affine, so then cohomology of HI x is 0 if I is greater than 0. So then we can compare with the local cohomology with the cohomology with the x minus point. So then HI, but x minus p, this OX is isomorphic to equals 0, and also this isomorphic to HIP x OX, actually P, not P, P plus 1, I plus 1. So then to checking the this vanishing, it is enough to checking the this vanishing, but if M is not 0, then actually we give a condition because the other side is the using the duality. So we need to check only the if this is 0 case, but that is HISO. But that so that is why this ST condition is the same as the vanishing of this cohomology. Okay. And then next one is the coming from the OY minus not. Okay, what's the y? So now we have this x, right? And then to s here. This is made by cone. But then we can resolve partial resolution of this singular point. So then we have a exceptional here, but which is isomorphic to the exceptional is isomorphic to this s. So then this OY minus E is the same as if this is pi, pi upper star A. Then computing the from the Z condition. So that gives us this is but then we have this relation, so that is y OY. Okay, and also you can check the converse direction. So that is why this satisfied, then this power is because then this push forward is exactly the omega xr. So that is why Q-Gorenstein condition is the same as that omega xr power is this A. But also, by using the duality, actually the omega x also satisfy ST. Is we can check as by the condition of the vanishing by using the duality. Okay. So anyway, this is the example which is does not satisfy Cohen-Macaulay, but satisfy the Q-Gorenstein. You can find many examples. Okay, so then now let me define the Q-Gorenstein morphism. Okay, so now suppose this is flat. And then also, always when we want to define this dualizing shift, we need to Gorenstein in codimension 1. So, but here we say that such that every fiber is Q-Gorenstein scheme. Okay. So then, I mean, each fiber we have this. This one by using the also push forward of the Gorenstein locus, but also we have this similarly as this one. Okay. So then we say the F is naively Q-Gorenstein at the point y if this at y for some okay. So naively Q-Gorenstein means that simply this dualizing shift is the line bundle. So this is usually called the P-Max conditions. So invertible condition. And then also we say the naively Q-Gorenstein at y means at the every point. And then also we say the F is Q-Gorenstein. Here we do not say naively, just Q-Gorenstein. If this is some open set neighborhood U of y such that this U over T some power is flat over T and satisfy S2 over T. It means any this fiber for any K or any K here. So these are called the Q-Gorenstein morphism. Okay.
I have a stupid question.
Yes.
Because I have seen different definitions for omega y over t, which are not.
So I will give you.
Which are not always the same if the fibers are not reduced. So what is the definition here? I mean, does the definition here commute with phase change or not?
Yeah, actually the second condition satisfies phase change. This is
Okay,
I want
so,
to say.
so
Yeah.
you
Yeah,
take
this
the-
is a polar
You
condition.
take definition. that
Yes,
commutes
yes,
with
yes, 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 sure, sure, sure. And then, yeah, I will also give you example the satisfy 1 but not satisfy 2. Actually, that is due to the Patak fiber.
And the difference in definition doesn't really matter anyway, because you suppose the central fiber is reduced. For this talk, we are always supposing central fiber is reduced anyway. You know?
Yeah, yes. Yes, later then, when we say Q-Gorenstein deformation, we only need to central fiber, yeah.
Yeah, so we can follow.
But this all definition can be generalized to the not just the scheme of a field. We can generalize much more too. Okay, so then also let me give you some remark, I think which already mentioned. So first one is the this virtually naively Q-Gorenstein can be checked rather easily. So why Q-Gorenstein? So sorry. So here we assume the T is Q-Gorenstein scheme. For example, DVR was some smooth scheme. So then why is Q-Gorenstein implies this naively Q-Gorenstein. Then, but this second one, so now F is flat, and then also satisfy the S2 morphism. S2 morphism means that each fiber satisfies S2, and then also all fibers are Gorenstein in codimension 1. And then suppose this YT is Q-Gorenstein. So now over T, so we have a one YT, and now we assume this is Q-Gorenstein. So then this morphism is Q-Gorenstein along this, given this YT is equivalent to satisfy the space change condition. Because we have this one, but then when we tensor this to the district to the central, but then also we have dualizing on the central power. So then we can compare these two. But in general, these two are not same. But if the satisfy that condition, Q-Gorenstein definition of this Q-Gorenstein, then satisfy this one for all K. So this is called the Gola condition. So this condition is especially very important to construct the moduli space, because if you have to construct moduli space, you're using some very high power of the dualizing, but then when you restrict to the each element, should be the same as this given dualizing shift. Okay. But then, unfortunately, this some naively Q-Gorenstein does not satisfy this Q-Gorenstein. Not Q-Gorenstein. So this is basically due to. So let me give an example. This one. So now choosing Z is a K3 surface. And then V is a non-singular just projective variety of dimension n-1, such that this dualizing is just OV. And also assume the HI V OV equals 0 for any -1. Just choose it that is non-singular variety. And then choosing the, also we will use a cone. So then choosing ample divisor, so smooth ample divisor on C cross V. And then A is again the ample divisor. And some high power of S, E. Is sufficiently large here. Basically, this to give some vanishing. So then, okay, so this is vanishing. Because actually, we do the same example of the previous. So to vanish of these two conditions. So this is 0. But then, I mean, these are just the product, so then we can see the this is non-zero exactly the when I is 0, 2, and -1, and +1. But then also there is another vanishing from the Kodaira vanishing. This is also 0. So any I equals 0. These are coming from Kodaira vanishing. So then from this construction, this S is coming from the ample divisor. So then, and then using this 3, so then we see the HIS OS is non-zero when I equal 0, 2, and -1. Okay, and then construct the using the cone, affine cone, by using this S. And then we see the data does not satisfy some ST conditions. Okay, so then consider again this cone. Okay, so then we have a map from X to A1 by using this cone. So this case, X satisfies S3 because of the using the just vanishing. Because the right. because H1 SOS equals 0, so that implies that we have a S3. And then, but depth is 2, because we can check also using the vanishing of cohomology, actually the depth of omega xt is less than 3, and then we can check that because Hn minus 1 is non-zero. But in this case, omega s e power from the construction, these are the same as A. So given this dualizing is the power of the A, implies the previously I said at the cone case, this implies the X is Q-Gorenstein. Then let H be a fiber through this singular point. Then this is invertible because we know the X is Q-Gorenstein, but this restrict this H to this phase change, but this is not in fact, so this satisfies S2, but this depth is only depth of this one is only 1. Okay, so we have some example which is satisfy the naively Q-Gorenstein, but not the Q-Gorenstein. Okay, but we have some hint here. Right? This depth is actually less than 3 here. Okay, so then so this is two definitions of naively Q-Gorenstein and the Q-Gorenstein. But then as a notion of Q-Gorenstein deformation, Hacking considered some deformation on the index 1 curve. So he considered the deformation which leads to an equivalent deformation on the index 1 curve in the case of the surface case. And then actually he showed that his definition satisfied the Gollas condition. So if we changing the original definition of Q-Gorenstein slightly different way, so then what happens? I would like to then study what happens. So now F is also flat, and then also each fiber satisfy Gorenstein. So each fiber is Q-Gorenstein in codimension 1. And then assume also the one fiber, this given fiber is Q-Gorenstein. At y, given some point y. And then we say the F is virtually Q-Gorenstein if there is some open neighborhood V of y and the coherent shape L coherent maybe sorry reflexive shape L such that if you're restricting this L to this neighbor, so then it's this dualizing shape. And then also satisfy for any k, this RK is flat over T and satisfy S2. So what's the difference between these two definitions? I mean, Q-Gorenstein and the virtually Q-Gorenstein is the here we do not say that this is coming from this omega. Just some reflexive coherent shift when restrict satisfy this one given this fiber, and then we have the same condition for L, not the dualizing shift. This is the difference between the virtually and the Q-Gorenstein. Because for example, if you define this Q-Gorenstein from using the index 1 cover, it might be this coming from the index 1 cover dualizing is not exactly the same as a given dualizing. So that is why we define in this way of the virtually Q-Gorenstein. But then also we can find the example which is virtually Q-Gorenstein but not the Q-Gorenstein. Yes, given this one and given, but we do not give any power is the same. We just say but yeah, actually if satisfy this, but only for the restriction, yes. But the power we did not say. But these conditions are same, right? Okay, maybe I will give this example if I have time. Maybe I will state some result first. So one, also from this example, what we can see is given one fiber is Q-Gorenstein, but this condition is not the open condition. So when we have a flat morphism and the central one fiber is Q-Gorenstein, but does not imply to the Q-Gorenstein to the open neighbor. About it?
It's bad that happens.
The example is something like choosing the curve in the peak 0 and through the identity point. So then central is the trivial shift, but the general is just algebraically equivalent to 0. Using that one, actually, we can see construct some example which is central is only Q-Gorenstein, but general is not.
No, I agree. But that's not bad.
Yeah?
You should not change the definition so that
No. But then I wanted to say some special condition, not so much special condition, gives actually virtually Q-Gorenstein implies Q-Gorenstein. Okay, so then. Actually, the kind of idea is something like similar as Schiller-Singers when he proved the quotient singularity is rigid. S3 condition is very important to prove this rigidity. So here we also say the S3 condition actually gives us. So, okay. Okay, so then what can we say? So now, so this is one theorem. So F is flat, and each fiber is Q-Gorenstein in codimension 1 and assume F is virtually Q-Gorenstein at every point of this given yt, then F is Q-Gorenstein along this given yt if yt satisfies S3. Okay, this is the one theorem. And then another picture. So this condition implies the virtually Q-Gorenstein, implies the Q-Gorenstein. So then another one is the F is flat. And then F is Q-Gorenstein along yt if the satisfy the following three conditions. So one is this, I mean, definitely given yt is Q-Gorenstein. It's a natural condition. And then second one is the rather stronger one. Yt is Gorenstein. But we know many examples in the surface case. So yt is Gorenstein in codimension 2. So surface case is not. So just surface case is Gorenstein. But we have many examples for higher dimension case. For example, isolate the singularity in 3-4. So then third one is this omega yt k any power satisfy S3. So this satisfy S3 for any k. So it's the same as the index 1 cover satisfy the S3 condition. It's same condition. So then we can say this morphism is Q-Gorenstein. The proof is coming from the first step is to reduce this problem to the Artinian local link. Because actually then we can to prove this. Actually, how we prove this Q-Gorenstein, just proved satisfying the Koller condition. So proving phase change condition. But then when we reduce to Artinian local link, then we can just show that each step by step of the lifting tool. So that then it works by these three conditions. Actually, this statement is also in someone's paper, but we do not understand his proof because he used some commuting with the projective limit and this open immersion, but this is not clear. If the map is proper, then this inverse limit is commuting with the proper morphism, but it's not clear to the open immersion with this inverse limit. Because we need to using some defining by this using the Gorenstein locals, and then we need to push forward of this using open immersion. But then if you do the only in the open locus for this statement, and then finally you need to by this push forward, but then you need to show this satisfying the commutative condition between the open immersion with the inverse limit. But this is not clear. So we do a rather different approach.
What is the output of this proof? Sorry.
I don't want to say the proof.
Okay.
Oh, this proof?
No, the proof you said you don't understand.
Which is, yeah, I don't want to say that.
Okay.
He's the big mathematician, and maybe he knows the proof, but just it's not clear. Open immersion and commuting with the inverse limit is not clear.
limit of the Artinian thing?
Oh yeah, here we're using the just lifting to the each this mn.
Yeah,
Yeah.
this inverse limit.
Yes, yes. This commute definitely. Yeah. Okay, so then let me define what's the Q-Gorenstein deformation. If this map is a Q-Gorenstein morphism along this, given this y, this 0, given this some fiber, then we say these are called the Q-Gorenstein deformation. So basically the definition is coming from the Q-Gorenstein morphism. So then from this theorem, actually, then we get the several corollaries. So for example, X is Q-Gorenstein scheme. And this is the deformation of X over a non-singular curve. And then assume this y is Q-Gorenstein, and any local index 1 cover of y satisfy S3, then this yt is also Q-Gorenstein. This is basically we can prove from the theorem. But then if we do in the characteristic k equals 0, and suppose this y, so it's same situation, but we have same. And then, but if suppose y has log terminal singularities, because in general, it's quite hard to check the local index 1 cover satisfy S3. It's still hard to check. It's not so much stronger condition, but it's still hard to check. But if this is characteristic equals 0 and this is log terminal, but then index 1 cover has a rational Gorenstein singularity. So in this case, index 1 cover has a rational Gorenstein singularity. We especially satisfy the Cohen-Macaulay conditions. So then satisfy the second one. So implies the yt is Q-Gorenstein. Just 5 minutes more? Can I do 5 minutes just more? Yeah.
You are assuming that the y is Q-Gorenstein vectors.
I say the corollary is the same condition as proposition. So given this X is Q-Gorenstein. Yes, yes. So this corollary said if we know some nice singularity of this full y, then we can see this Q-Gorenstein. But maybe best result is only related with not y, only related with the condition of the x, right? Okay, so then state one theorem. Now X is normal variety with only canonical singularity. And but here also characteristic 0. And then now YT is the deformation of the, so this deformation of the non-singular curve. Then this is Q-Gorenstein. Q-Gorenstein deformation. So canonical singularity case always over non-singular curve is the Q-Gorenstein deformation.
Is this really new characteristic zero?
Yes, because for example, there also we use something like a log terminal case. We use index 1 kappa is rational Gorenstein. This kind of result.
But I mean, you are like comparing, for example, positive characteristic.
So anyway, in this proof we use the same result, index 1 kappa.
Positive characteristic, you don't know or you are characteristic?
Yeah, I don't know anything about this kind of index 1 kappa satisfy what kind of singularity. Actually, even index 1 kappa is quite complicated because if the characteristic, yes. Okay, so first way is to using the Kawamata's result. So this maybe say the proof 1 is using Kawamata's big result. What he proved is if you have a canonical singularity and then deformation of this curve, then this is also canonical singularity. So then Y is canonical. But then I mean we have the same result because then using the index 1 cover, so then index 1 cover satisfy this Cohen-Macaulay condition. And also canonical, here we're choosing the canonical singularity, so X is canonical, so implies the Gorenstein in codimension 2. I mean, terminal singularity then is non-singular in codimension 2, but canonical implies the also same as using the cut back to the surface, but then we have the same result than Gorenstein in codimension 2. So then using this theorem said that if we satisfy these three conditions, then it's Q-Gorenstein. So then by our previous theorem implies this result. But also the other way is we can use it directly without using Kawamata's result, because sorry, actually here I do not need this one. Sorry. Actually, this, maybe I need this. Sorry. Yeah, we have a three condition was here, Q-Gorenstein and Gorenstein in codimension 2 and satisfy S3. So then we can use directly this theorem. So we know this from X is Gorenstein in codimension 2. And then here, actually, we do not need to this S3 condition for the Y. Only we need the S3 condition for this X. So then also we know the local this index 1 cover of X. Here local index, this index 1 cover of Y, but here we're using index 1 cover of X. But here canonical singularity, so we can use the same result. So then this is also satisfy this Cohen-Macaulay condition, and then using the theorem, we get the same result. Okay. So the canonical case, I mean, we do not need to worry about the Q-Gorenstein for the deformation to this non-singular curve. And then maybe let me just write the final corollary. Is X is Q-Gorenstein scheme over K, and suppose X is Gorenstein in codimension 2, and any local index 1 cover. Actually, in the K-testic 0 case, we need to check just one cover. But for positive K-testic, we need to check any local index 1 cover of X satisfies S3. Then any deformation is Gorenstein. Here we do not need a characteristic 0 because this is simply the coming from this theorem. So then also another one is now X is also same. X is the Q-Gorenstein scheme over K, and then suppose dimension is larger than or equal to 3, and X is isolated singularity. So then any deformation of X is Q-Gorenstein if this index 1 cover satisfies S3. So the same, this condition. Yeah. Okay. So basically what here I want to say is to satisfy the index 1 cover satisfy this condition, and the codimension 2, Gorenstein codimension 2 case, we do not need to worry about the Q-Gorenstein things. So surface case, I mean, definitely this is not true. I mean, if you have a normal surface with singularity, then definitely not Gorenstein codimension 2. But if you're going higher dimension, so then isolate the singularity with this rather mild condition, then always Q-Gorenstein. We don't need to worry about the Q-Gorenstein thing. Let me stop.
Any questions, Imad?
So what in your general theory in mixed characteristic, you say you're going to make something interesting in characteristic.
Okay, so now one application is the first we can prove the kind of Q-Gorenstein deformation functor is nice properties, same as usual deformation functor. This is one, and then more explicit application is we can apply this Q-Gorenstein deformation theory to some surface in positive characteristic using this mixed, maybe not this one, but but we still do not find some explicit example application to the, for example, threefold case or higher dimension case. We have some theory, but still, yeah, we need to work. But anyway, our approach does not relate with this positive characteristic, so maybe we can apply to also positive characteristic.
And your last corollary, you're supposing that X at least 3 and isolated singularities. Now, if we assume that the singularities are quotient singularities, we have this theorem of
yes, but then it's
rigid.
rigid, right.
And so you can say something more, or?
No, that case, nothing. I mean, rigid, so we don't need to worry. But terminal singularity is not quotient, not only quotient singularity. Sano has studied this Pano with the terminal singularity, right? So because sometimes it's rather hard to check a Q-Gorenstein condition if we want to check directly. But just what we want to say is in most cases you don't need to check. This is what we want to say. No. We cannot prove the directly canonical, right? Oh, yeah. This proof too, we do not need to use Kawamata's result. Yes. We can just using directly from the. Why? No. I don't think so. Yeah. Because, for example, rational, this log terminal index 1 cover is also satisfied quite Macaulay. So this does not imply the canonical. Right? No. So it does not, because the canonical need a more stronger condition, right, for the singularities. Does not say that. Only the Q-Gorenstein condition.
If you think about moduli, say of canonical threefolds, then you prove that Q-Gorenstein deformations and its usual deformations are actually the same.
Yes.
I was wondering, maybe it's a general question, is there something known, like in this case of surface Hall deformations of the minimal model and the canonical model compare? It's probably a completely different story.
Yeah, I think that it's different story. What we can say is something like the canonical threefold, and then if you do this deformation theory, using deformation theory, maybe you can construct the moduli space is just the Artin stack. If you have a good theory for Q-Gorenstein, something like a Q-Gorenstein satisfied these versatility conditions. So then maybe you can say only this moduli space using only the deformation theory, then it can say that these are something like Artin stacks. But we cannot compare with the minimal model theory. And
No, so I was thinking, no, you could be right. I mean, maybe it's not so hard to get from 2 to 1.
are you saying that?
It seems quite possible.
You mean Q-Gorenstein, then there is what's that? This same condition to canonical? Okay, yeah, let us discuss.
So you said there is no application of, I mean, you didn't find any interesting example of threefolds with
Yeah, right. So something like similar as a surface if I construct some strange threefold, and then we want maybe to prove the existence of deformation. But then question is how to check a Q-Gorenstein, this deformation. But then what we say, under some condition, this Q-Gorenstein coming directly. This is what we want to do, but I did not apply it yet.
So let's take this figure again.